In the marvelous unfurling of the cutting-edge universe, individuals have long investigated whether we're remote from each other. We've looked at the stars, inspected the tremendous designs of cosmic systems, and left determined to find the potential for life beyond our little blue planet. That potential has finally come to completion. As of late, NASA's chief scientist revealed that the James Webb Space Telescope, our window to the universe, has decided something super, prepare yourself for this, on the edges of our unlimited time. A staggering secret has been uncovered. Life has been identified on a world referred to as Proxima B, and it changes everything. The examination of the environments of exoplanets that pass in front of their stars obliges us as we unveil the secrets uncovered by the James Webb Telescope. What could the revelation of life on Proxima B mean for the future of space exploration and humanity? The James Webb Space Telescope is a wonder that promises to change how we understand the universe. The telescope's advanced technology, combined with its unique position in space, gives researchers an unparalleled viewpoint on the universe. It allows them to focus on distant cosmic designs, planets, and stars in ways that were never possible before. Now, this could seem like a lot of empty promises, but it's got the tech to make all of that real. One of JWST's most important features is its primary mirror, which measures 6.5 meters in diameter. This is over 2 times the size of the primary mirror on the Hubble Space Telescope, which has been one of the most critical tools for space exploration over the last few decades. With such a large mirror, JWST can capture the faintest glimmers of light from the farthest reaches of the universe, features that the field of science has never been able to observe before. Researchers have long speculated about what lies beyond the limits of a regular telescope, but with this one, they can finally see the true details they've been dreaming about for so long. It's not just its enormous mirror. The JWST is equipped with a set of cutting-edge instruments capable of detecting a wide range of light frequencies. The near-infrared camera, NIRCam, as it's often called, is an essential tool designed to capture images in the near-infrared section of the electromagnetic spectrum. Why is that important? Well, near-infrared light can penetrate dust clouds that block visible light, allowing us to see deeper into the vastness of space. NIRCam's high-resolution imaging abilities provide astronomers with an unprecedented view to examine the formation of stars and galaxies. This remarkable instrument's primary targets include focusing on the early universe, its first light, the structure and evolution of galaxies, and the detection and characterization of exoplanets. The detailed pictures captured by NIRCam reveal hidden details and structures that were previously out of reach for telescopes. It helps us understand how massive structures form and evolve over time and provides insights into the mysterious processes that shape our infinite expanse. But that's just one tool. There's also the near-infrared spectrograph, NIRSpec, which takes the study of stars and cosmic systems to an unimaginable level by separating the light emitted by celestial objects into its component colors or frequencies. This process, called spectroscopy, provides key data about the chemical composition, temperature, and evolution of these objects, helping astronomers analyze the intricate details of stars and galaxies. It gives researchers accurate insights into everything it observes. By focusing on the absorption and emission lines in the spectra, analysts can identify the elements present in a star or gas cloud, revealing the building blocks of our universe. This information helps us understand the life cycles of stars, the evolution of galaxies, and the complex relationships between celestial bodies. On top of that, NIRSpec also plays an important role in studying distant, high-redshift galaxies. These universes emit light that has traveled billions of years to reach us, offering a glimpse into the origins of the universe. Examining their spectra helps astronomers understand their chemical makeup, age, and other properties, shedding light on the overall development of galaxies throughout cosmic history. Regarding the mid-infrared region of the electromagnetic spectrum, the mid-infrared instrument, MIRI, on the JWST has been specifically designed to analyze objects emitting infrared radiation at longer wavelengths. This ability allows us to investigate a variety of phenomena, from the formation of stars to the detection of exoplanet atmospheres. One of MIRI's primary objectives is to study the dust clouds where stars are born. Infrared radiation can penetrate these dense dust clouds, allowing MIRI to see through the cosmic fog and observe the birth of stars and planetary systems. It captures detailed images and spectra in the mid-infrared, providing astronomers with critical insights into the processes happening within these stellar nurseries. But that's not all. MIRI also plays a crucial role in the search for and characterization of exoplanets. It does so by observing in the mid-infrared, as this enables MIRI to detect and analyze the faint thermal emissions of exoplanet atmospheres. This capability opens up opportunities for studying the composition, temperature, and characteristics of exoplanets, including their potential habitability. MIRI's observations help us determine the presence of water vapor, carbon dioxide, and other key molecules that could indicate the conditions necessary for life. These are just the elements that could support life. How does the James Webb Telescope search for signs of something happening beneath the surface? Two of the primary methods it uses are spectroscopy and transit observation. At the heart of this work lies spectroscopy, a technique that allows researchers to examine the light emitted or absorbed by an object to determine its composition. In the context of exoplanets, spectroscopy helps us interpret the atomic secrets hidden within their atmospheres. When the JWST sets its sights on an exoplanet, it eagerly waits for a transit event, or rare occurrence where the exoplanet passes in front of its host star from our perspective. As this happens, the JWST observes the starlight filtering through the exoplanet's atmosphere during the transit. Equipped with its advanced instruments, the JWST captures this crucial light. NIR-SPEC excels in the near-infrared range, while MIRI takes over in the mid-infrared domain. Together, they form a dynamic duo, covering a wide range of frequencies essential for in-depth investigation. Travel well, this strait contains essential data about the exoplanet's climatic arrangement. As the light goes through the exoplanet's climate, it communicates with different atoms present, leaving particular fingerprints or atomic engravings on the strait. The JWST then carefully examines the sifted light, utilizing its spectroscopic capacities. Researchers can identify explicit particles present in the exoplanet's climate by examining the absorption particle or discharge lines in the light spectrum. Each particle has its unique arrangement of ghostly features, so every one of them has their own characters. They simply have to be identified and recorded to bring the entire story reasonably together. To get precise results, the JWST conducts broad modeling and analysis. It depends on complex simulations and reference spectra of known atoms to match the noticed ghastly elements with their corresponding atomic characters. Think about it like cross-referencing a heavenly word dictionary to interpret the exoplanet's barometrical language. Identifying the presence of explicit particles is only the beginning. The quest for indications of something going on under the surface requires a more nuanced approach. Researchers search for atoms considered biomarkers, substances that could be related to life. These biomarkers could include gases like oxygen, methane, and water vapor, elements essential for supporting life on Earth. However, more insights and data are needed to evaluate the general tenability and potential indications of biological activity. To improve the search for life, the JWST also supplements its spectroscopic abilities with other observational procedures. Within the extraordinary breadth of the universe, people have long questioned whether we're alone. We've looked at the stars, analyzed distant systems, and set off on a journey to find the potential for life beyond our little blue planet. That potential has finally been realized. NASA's administrator recently revealed that the James Webb Space Telescope, our window to the universe, has tracked down something extraordinary. Brace yourself, for on the edges of our vast time, an incredible secret has been uncovered. Life has been seen on a world called Proxima B, and it changes everything. The examination of the environments of exoplanets that pass before their star allows us to reveal the secrets uncovered by the James Webb Telescope. What does the discovery of life on Proxima B mean for the possible future of space exploration and all of humanity? The James Webb Space Telescope is a scientific wonder that promises to change how we interpret the universe. The telescope's refined development, combined with its unique role in space, gives specialists a remarkable point on the universe and allows them to focus on far-off infinite systems, planets, and stars in a way that has never been possible before. Now, this might seem like a part of void cases, but it actually has the tech to make all of that real. One of JWST's most super parts is its primary mirror, which measures 6.5 meters in diameter. This is over twice the length of the primary mirror on the Hubble Space Telescope, which has been one of the most significant tools for space exploration in recent years. With such a large mirror, the JWST can catch the smallest flickers of light from the most distant parts of the universe, elements that the world of science hasn't consistently had the capacity to see. Specialists have long hypothesized about what lies beyond the limits of a conventional telescope, but with this one, they can finally see the real detail they've been dreaming about. Not just its huge mirror, the JWST is equipped with a variety of cutting-edge instruments that can detect a wide array of frequencies of light. The near-infrared camera, NIRCam, as it's typically known, is a priceless asset designed to capture images in the near-infrared range of the electromagnetic spectrum. Why is that important? Well, near-infrared light can penetrate dust clouds that block visible light, allowing us to see further into the boundless depths of space. NIRCam's high-resolution imaging abilities provide space experts with an unmatched view to analyze the development of stars and systems. This exact instrument's primary targets include focusing on the early universe and its first light, investigating the formation and development of galaxies, and identifying and describing exoplanets. The detailed depictions captured with the help of NIRCam reveal hidden nuances and designs that were previously out of reach to telescopes. It enables us to perceive how large systems form and grow over time, and provides insights into the mysterious processes that shape our vast realm and beyond. But that's just one tool. There is also the near-infrared spectrograph, NIRSpec, which takes the assessment of stars and cosmic systems to an exceptional level by isolating the light produced by divine things into its component tones or frequencies. This technique, known as spectroscopy, provides invaluable records about the chemical composition, temperature, and movement of these things, enhancing astronomers' ability to detect the unpredictable functions of stars and systems. It offers scientists detailed insights into everything it observes. By analyzing the absorption and emission lines in the spectra, researchers can determine the elements found in a star or gas cloud, revealing the building blocks of our universe. This data enables us to understand the life cycles of stars, the development of galaxies, and the intricate relationships between these heavenly parts. Furthermore, the near-infrared spectrograph plays a vital role in the study of distant, high-redshift galaxies. These galaxies emit light that has traveled billions of years to reach us, providing a glimpse into the beginnings of the universe. By investigating their spectra, space researchers can start to understand their chemical structure, age, and other attributes, providing insights into the overall development of galaxies over time. Astronomical history, with respect to perusing the mid-infrared area of the electromagnetic range, has seen significant advancements. The mid-infrared instrument, MIRI, on the James Webb Space Telescope, JWST, has been explicitly designed to investigate objects emitting infrared radiation at longer frequencies. This ability permits us to explore various phenomena, from the development of stars to the detection of exoplanet atmospheres. One of MIRI's essential objectives is to study the dusty regions where stars are conceived. Infrared radiation can penetrate these thick dust clouds, allowing MIRI to look through the cosmic haze and witness the formation of stars and planetary systems. It captures detailed images and spectra within the mid-infrared range, offering astronomers critical insights into the processes occurring within these celestial nurseries. However, this isn't all. MIRI also plays a major role in the search for and characterization of exoplanets. It does so by observing the mid-infrared, which enables MIRI to detect and study the weak thermal emissions from exoplanet atmospheres. This capability opens up opportunities to study the composition, temperature, and characteristics of exoplanets, such as their potential habitability. MIRI's observations help us in determining the presence of water vapor, carbon dioxide, and other key molecules that could suggest conditions favorable for life. Taking everything into account, these are only some of the factors that could support life. But how does the James Webb Space Telescope look for indications of something happening beneath the surface? Two of the essential methods it uses are spectroscopy and transit observations. At the core of this work lies spectroscopy, a technique that allows researchers to study the light emitted or absorbed by an object to determine its composition. With respect to exoplanets, spectroscopy aids in uncovering the molecular secrets hidden within their atmospheres. When the JWST focuses on an exoplanet, it eagerly waits for a transit event, a spectacular moment when the exoplanet passes in front of its host star, as seen from our perspective. During this event, the JWST essentially observes the starlight passing through the exoplanet's atmosphere. Equipped with its advanced instruments, the JWST captures this crucial light. The near-infrared (NIR) spectrometer excels in the near-infrared range, while MIRI takes responsibility in the mid-infrared domain. Together, they form a dynamic duo, covering a broad spectrum of frequencies that are essential for in-depth analysis. You may be wondering, what's the big deal about observing starlight during a transit? Well, this starlight contains vital information about the exoplanet's atmospheric structure. As the light passes through the exoplanet's atmosphere, it interacts with various molecules, leaving specific fingerprints or molecular signatures on the starlight. The JWST then carefully analyzes the filtered light using its spectroscopic capabilities. Researchers can identify specific molecules present in the exoplanet's atmosphere by examining the absorption or emission lines in the light spectrum. Each molecule has its unique set of spectral features, so every one of them has its own identity. They just need to be identified and recorded to piece the entire story together. To obtain accurate results, the JWST conducts extensive modeling and analysis. It relies on complex simulations and reference spectra of known molecules to match the observed spectral features with their corresponding molecular identities. Think of it as cross-referencing a cosmic dictionary to decipher the exoplanet's atmospheric language. Identifying the presence of specific molecules is just the beginning. The search for signs of life requires a more nuanced approach. Researchers look for molecules known as biomarkers, substances that could be associated with life. These biomarkers could include gases like oxygen, methane, and water vapor, essential elements for sustaining life on Earth. However, more data and insights are needed to assess the overall habitability and potential signs of biological activity. To enhance the search for life, the JWST also supplements its spectroscopic capabilities with other observational techniques.